Electric circuits are the invisible highways powering everything from your phone to entire cities. In this video, we'll uncover how charge flows, how resistors and capacitors affect that flow, and what makes a circuit tick. Whether you're building a robot or just flipping a light switch, it all starts with the fundamentals of circuits. An electrical circuit is a closed path through which electricity can flow. A simple circuit just has several key components. First, a simple circuit will have a voltage source. This is something like a battery, which motivates charges to move through the circuit. Without a voltage source, there's no reason for the charges to move. We know that charges want to move from high potential to low potential if they're positively charged, so a voltage source is needed to have a current. And the current will always flow from the positive end of a battery, that's where there's high potential, to the negative end of a battery, where there's low potential. Then we'll have a set of wires that connect these electrical components. Usually a wire is something with very low resistance, so we would expect that there would be no potential drop across that material. And then a circuit will have some type of resistive load. In this case, we call that a resistor, which ultimately limits the flow of electricity by dissipating some of the electrical energy of the circuit into the form of heat or light. Finally, a switch can be incorporated such that you can open or close the switch, allowing for the electricity to have a closed loop path. When the switch is flipped down, we would say that the switch is closed, and this means that electricity can flow because there's an electrical connection between conductors. However, if the switch was instead open, the electricity would not have a closed loop path to follow through these conductors, so no electricity would flow and no current would be flowing when a switch is open. We can use a circuit diagram to represent the different components in a circuit, and all of these different circuit elements have a specific symbol that we use to draw up these circuit diagrams. For example, our battery would be like a voltage source, and we would use this symbol for a battery. So you're going to get used to using that one a lot, where the long end of this symbol has a positive sign, and that is the positive terminal of the battery. That's a location with high electric potential, and the end of the battery, the negative end, would be a shorter line, and that would be where the electrical circuit ends. However, we could also use other symbols to represent different circuit elements. For example, a resistor, which would dissipate electrical energy from the circuit and give it off as heat, or a wire, which would just allow for electric current to flow freely from one circuit element to another. Here's the symbol for a switch, which is like a gate that could be open like you see here, or we could draw it with a straight line connecting those 2 points, meaning that it's closed and the electricity has a closed loop path to follow. A capacitor looks like two straight lines parallel with each other, as if it's two capacitor plates charging up with opposite charge. And then we also have other types of circuit components that we'll continue to talk about later. On the right side, you will see a simple circuit diagram of just a battery and a resistor. This is like if I hook up a battery to a light bulb. And you can see that we have this closed loop path with wires connecting the different circuit components. Here's our resistor connected with wires to our battery. In this case, this circuit diagram represents a flow of positive charges from the positive terminal of the battery through the circuit, powering on the resistor until that electricity finishes its closed loop path at the point of low potential, the negative terminal of the battery. And it's important to note that the actual orientation and length of lines in these circuit diagrams does not matter. It doesn't matter if I put the battery up on top over here, or if I put the battery on bottom and the resistor on top. All that really matters is the order of these circuit components. You always want to trace where the electricity would go, thinking about the motion of positive charges. The conventional current I is following the path that positive charges would flow in, and so our positive charges leave the positive terminal of the battery, go through the circuit, and end at the negative terminal. Previously, we've spoken about how electricity can be viewed as being analogous to fluids flowing through a fluid system, where the voltage of our electrical circuit is essentially the pressure that motivates our electric fluid to flow through the system. The conductors of our electric circuit are like the pipes and tubes that connect a fluid system. The resistors are like an area of that pipe or fluid channel that is restricted, preventing free flow of electric fluid through the circuit. And switches are like some type of valve that we could open or close, allowing for the electric fluid to flow or not flow. There are really two ways that we can connect circuit components. The simplest way to think about connections is in a series connection. If our circuit elements are connected in series, that means that they are connected one after the other, such that electricity has to flow through the first component before it can flow through the next component. These are all sequentially in a linear order, one circuit element after the other, and so the electricity in this set of series resistors has to enter the first resistor before it can go through the second, and so on. The same type of arrangement could be made with capacitors in a circuit, where we have a bunch of capacitors one after another, and the way we connect these circuit components will affect the way electricity flows through that circuit. Based on the conservation of charge and continuity of flow, we know that for objects that are connected in series, that the current that would be being output by the battery has to equal the current going through the first component, has to equal the current going through the second component, and so on. This is because if we have circuit elements in a line, essentially the charge has to go through one before it goes through the next, and there's nowhere else for that current to go. It's not like it can leak out of the sides. The electric charge is going to stay localized inside of the conductor through which it is traveling. And by conservation of energy, we know that the power output by a battery, a voltage source, has to equal the power that's being dissipated by the entire circuit. So essentially, the power output by our battery will be equal to the power dissipated by any circuit component inside of our circuit. The elements that dissipate energy are the resistors. So if we have a battery, the output of that battery, the power output, must be the same as the power dissipated by all of the resistors in a series. This means that the total voltage in a series circuit will be the sum of the voltages across each circuit element, added together based on how many elements you have. For an electrical circuit with many resistors in series with one another, we can calculate the equivalent resistance of the entire circuit as if each of those individual resistors in series was combined or simplified to be one very large resistor. In this case, the equivalent resistance of this series of resistors would simply be the addition of the resistance value for each individual resistor in the line. And the same relationships from the previous slide will hold. The current traveling through each resistor in a line or in a series will be the same current. Whatever goes in one end has to come out the other. However, the voltage across each individual resistor will add up to equal the voltage output by the voltage source, the battery. So very often we will end up taking a complicated circuit that has multiple resistors in series with one another, and we will redraw it as an equivalent resistor circuit, where we combine each resistor, R1, R2, and R3, into a series resistor with the equivalent resistance of the total of them all added together. Notice again that it does not matter the orientation that we draw these resistors in. All that matters is how the electricity flows through that circuit. It will flow out of the positive end of the battery and around according to this blue arrow, so it will hit resistor 1, then 2, then 3 before making it to the end of the circuit. On the other hand, the capacitance for many capacitors in series is not so straightforward. If we have multiple capacitors in series with one another, such that the electricity essentially has to charge up the first capacitor before the electricity can go charge up the second capacitor and then the third one, in this case, we could calculate an equivalent capacitance of the entire series of capacitors as the reciprocal of the inverse value of each individual capacitance. That means that if we have 3 capacitors in a line, we will take the inverse of the first capacitance, add it together with the inverse of the second, and so on. And then once we get an inverse capacitance inside of these parentheses, you will then reinvert that total such that you can get it back into the units for capacitance, and this would be the equivalent capacitance of a series capacitor. Similarly, we can draw our circuit with several capacitors in a line. Here we have our battery supplying current to 3 capacitors in series with one another. We could redraw that circuit diagram such that we have just the battery going to one capacitor with a equivalent capacitance value of the entire series of each individual capacitor. You could think about this as being like separating the plates of our capacitor a greater distance. If the capacitance has a capacitor with a greater distance between the plates, then we would expect for the overall capacitance to decrease as we put more capacitors in a series with one another. Now, you don't actually need to draw your circuit diagrams with the capacitor plates farther apart. This is just meant to get the point across. You can always still just redraw your capacitor as the standard capacitance symbol. Just make sure you label it with the right value. Other circuit elements will affect each other when they are in series with one another too. For example, for batteries, if we put one battery on top of another such that the positive end is directly up against the negative end of the other battery, we would say these batteries are in series with one another. And essentially, this increases the total voltage supplied to the circuit. And that means that our total battery voltage that we supply to that circuit would be the addition of each individual battery in series with one another. And again, the same rules for series components holds. This means that the current from the batteries in series with each other will still always be the same current as one individual battery, but they will supply a greater voltage. So let's try an example. Here we have a simple circuit with a battery. Sometimes that would be labeled as epsilon, but really that is just the voltage supplied by our battery. Electricity will flow out of the positive end of this battery through the first resistor, through the second resistor, until the positive charges make it to the end of the circuit at the negative end of the battery. We're given a few values for these circuit elements. Resistor 1 is at 6 ohms and resistor 2 has a resistance of 4 ohms, and the battery supplies 5 volts to the entire circuit. So for resistors in series, we know that the voltage supplied by the battery will end up equaling the voltage across resistor 1 plus the voltage across resistor 2. All of the voltage supplied by the battery has to be dissipated by all of the resistors in the series. It's like we're labeling the end of our circuit as V equals 0 and the beginning of our circuit as some battery voltage value. Now, we were told that the voltage of our battery is 5 volts, but we do not know the voltage drop across each individual resistor. However, we do know Ohm's law, and Ohm's law says V equals IR for some resistive component. So we could instead substitute that. V1 is I1 R1 and V2 is I2 R2. We know what the resistance values are, but we do not know what the value of these two currents are, but we can say for sure that the current flowing through resistor 1 will be equal to the current flowing through resistor 2. These two values should be equal if they're in series with one another. So if we can figure out what that current value is, we can figure out everything that we need to know about this circuit. Almost every time that you have a combination of circuit elements in series or parallel with each other, you will want to draw an equivalent circuit that has a resistance that is equivalent to all the resistors in the series. That means you will take your circuit diagram here and you will redraw it such that all of the resistors in series are combined. So we'll always start with our battery. I like to label the positive end and the negative end, and then we will continue drawing our circuit elements in order. And if we were to combine resistor 1 and 2, it would be like there was only one resistor left, and this resistor we could say has the equivalent resistance of the series of 1 and 2 combined. For resistors in series, it's pretty straightforward to find the equivalent resistance. R of 1 and 2 combined would just be the resistance of 1 plus the resistance of 2. In this case, my equivalent resistance for this series is 10 ohms in total. And now if you take a look at our diagram that we drew with the simplified equivalent resistance, you can see that we just have one resistor with one battery. It should be possible to figure out the current through this simply using Ohm's law. We have our battery supplying a voltage that will end up being dissipated by all of the resistors in the line. The voltage across 1 and 2 combined has to be equal to the voltage that is sent out by the battery. And so the current through resistors 1 and 2 will be the same, and it will be based on the total resistance of 1 and 2 combined. In this way, we can rearrange and solve for the current of our entire equivalent resistor. In this case, we find that the total current flowing out of our battery and through all of our system all at the same time is 0.5 amps. And so if we know the current, we should be able to figure out the voltage across each resistor. The voltage across resistor 1 will be I1R1. It would be 0.5 times R1. That would be 3 volts is dissipated through the first resistor. And for the second resistor, it would be I2, R2. But we don't really need to worry about that 2 subscript for the I because we know the current is the same through all of these elements. And that means that the current times the resistance for resistor 2 would give us a value of 2 volts that was dissipated across resistor 2. So resistor 2 dissipates 2 volts from the battery, and resistor 1 dissipates 3 volts from the battery, and this totals the output originally put out by our voltage source. In this case, we took 2 series resistors and calculated the equivalent total resistance of the entire circuit. So that was for circuit elements that are connected in series with each other. But we can also connect circuit elements in parallel with each other such that the electricity flows through both circuit elements at the same time, not one after another, but taking 2 separate paths to go through different circuit elements. This is called a parallel connection. And in this case, parallel resistors might look like we have electricity coming into this junction point and then splitting as it goes down each individual path, dispersing the current along each path until it eventually comes back together at the end junction point. And we know from our previous understanding of electric current that whatever current is entering the junction has to be equal to the current that is exiting the junction as well. This ultimately means that the total current output by our voltage source battery is going to be the current across each path of a parallel connection. However, the potential difference between the 2 points of the junction at the start and at the end will always be the same regardless of which path you take. The voltage drop across each individual path in a parallel connection is equal. You'll notice that this is the opposite type of arrangement that we had for series circuit elements. So there are also rules for calculating the equivalent resistance of parallel resistors. And so if we think about electricity flowing into this parallel connection with 4 resistors, we can calculate the equivalent resistance of that circuit by redrawing it as an equivalent circuit, and we can calculate the equivalent resistance of a parallel connection of resistors using the inverse addition rule. This was basically the same formula for the capacitance in series, except for now we have resistors in parallel. And the idea is that for each resistor that we have in parallel, we will invert the individual resistance values, add them together, and then re-invert the total of what we get in the parentheses there to get it back into units of ohms and figure out the total resistance of a parallel connection. Remember, the voltage will be the same across each of these paths, but the current will not necessarily be the same. The electricity will follow the path of least resistance. In other words, the less resistance that a path has, the greater the current will be for the same potential difference across a parallel path. And if we were going to redraw these parallel resistors 1, 2, and 3 as an equivalent circuit, we could just simply redraw it as a simple circuit diagram with 1 resistor labeled with a specific label saying that it's got the equivalent resistance of all those individuals. For capacitors in parallel, the total equivalent capacitance will be the sum of every individual capacitor in the parallel connection. Here we have 3 capacitors, and essentially this means that if we have capacitors in parallel, we can store up more charge for the same given potential difference. We could redraw this circuit with 3 parallel capacitors as an equivalent circuit. And if you wanted to imagine it, instead of having our plates being farther apart like they were in series, in parallel, it's like our capacitors will have a greater plate area. And so overall, as we connect more capacitors in parallel with each other, the area effectively increases of the total entire capacitor system, and this would increase the total capacitance. It is also possible to connect batteries in parallel with each other. Essentially, when batteries are connected in parallel, they will supply the same voltage, that's the rules for parallel circuits, but their current will end up being additive for each parallel addition of another battery. So the same total voltage would be supplied to the circuit, but we would be able to deliver a larger amount of current. We could push more charge through in a shorter amount of time if we have many batteries in parallel with each other. So here we are with an example for resistors in parallel with one another. Here is our circuit drawn for us. We have the positive end of the voltage source and the negative end marked, and we trace the direction that positive charges would move. And if we do not hit a series of circuit elements and instead hit a junction point, we know that we're going to need to use the parallel circuit rules. One thing that I like to do as a little trick is sort of mark each junction with a special symbol so that you can know exactly where it begins and ends. I like to put a little star at the beginning and a little star at the end of my junction where the current splits and then where it comes back together, put a special symbol. And so the current as it enters into this junction could take path 1 through resistor 1, or the current could split into path 2 and take that path. And however much current flows through each path will depend on the individual resistance values, but we know whatever current enters at this junction point needs to equal the total current, making it back into the end of that junction so that the charges can eventually make it to the end of the circuit. We were given the values of R1 and R2, 6 ohms and 3 ohms, and we are powered by a 12-volt battery this time. So usually for these types of problems, it's always good to start by drawing an equivalent circuit. The equivalent circuit for 2 resistors in parallel can be drawn like so. We want to make sure we always start with our battery, labeling the positive and the negative end, and it's like we are going to combine these 2 resistors as if they're one resistor. This is the equivalent resistor with the total resistance of both of those individual paths, and you could call this whatever naming convention you want, but I like to usually do R parallel between 1 and 2, RP 1, 2. And so I know that R parallel for resistor 1, 2 is going to be the addition of the inverse resistance values reinverted in the end. In this case, we see that the total equivalent resistance of these 2 resistors in parallel with one another is just 2 ohms. As we open up more paths for the current to flow through, the total resistance of the circuit actually decreases. By adding more resistors in parallel, we decrease the total resistance of the circuit. So we were asked to find the current through each resistor in this case, and we know those currents will be different because the electricity will follow the path of least resistance. Without even doing any calculating, I predict that the current flowing through resistor 2 will be greater than the current flowing through resistor 1 because resistor 2 has a lower resistance. And we're also asked to calculate the total resistance. We did that. That's the box down in the bottom right. The total resistance of this parallel circuit is a equivalent resistance of 1 and 2 in parallel with each other. That answer is 2 ohms. So to figure out the current going through each resistor, we need to essentially figure out the current that is being output by our battery. And we know that that battery will output the same current as what is flowing through both the parallel paths that it could flow through. Once again, thinking about Ohm's law, we can substitute for an unknown variable with other known values. The current being output by our battery will end up being the voltage of our battery divided by the total resistance of the circuit, as if we were just looking at our simplified equivalent circuit right here. The voltage supplied by the battery must be taken care of by all of this entire resistor. And so that will end up giving us a current value that's output by our battery. The current from our battery will be 12 volts divided by 2 ohms. It'll be 6 amps. So we can say that those 6 amps are going to be equal to the amount of current going through the first resistor and the second resistor. And using Ohm's law, we know what the voltage drop is down either path. Whether we take path 1 or 2, we know that we'll start off at 12 volts at this junction point, and by the time we go through either path, we will need to end at 0 volts. The negative end of our terminal is essentially 0 volts, and no potential is lost as electricity travels through these wires. So all of that potential must be lost through each resistor path. And that means that the voltage through resistor 1 divided by its resistance value plus the voltage from resistor 2 divided by its resistance value has to add up to equal the current output by the battery. We can figure out the current through resistor 1 is V1 over R1. The voltage 1 and voltage 2 across resistor 1 and 2 are equal because these are in parallel with one another. So 12 volts will be lost across resistor 1 with its 6 ohm value, and that means that our current will end up being 2 amps through resistor 1. And through resistor 2, we would take the voltage of the circuit and divide it by resistor 2. That's 12 volts divided by 3 ohms. And we would see that we get 4 amps for resistor 2, 2 amps for resistor 1. Is that what we predicted in the start? We predicted that resistor 2 would have a greater current because it has a lower resistance, and we predicted that the current would be lesser in resistor 1 because it's got a greater resistance. And so everything is adding up, and you'll see that our 2 amps and 4 amps do add up to the total of 6 amps output by the battery. So let's try a little bit more complicated of an example. In this case, we have 4 resistors, each with different resistance values, and a battery supplying 10 volts to the circuit. We're asked to calculate the power dissipated in each resistor. That's the power dissipated by resistor 1, 2, 3, and 4 separately. But this circuit has a mixture of series and parallel connections. So we're going to need to simplify it by drawing equivalent circuits. First, let's think about the way the charges would move through this circuit. They leave the positive end of the battery and hit resistor 1 first, and then the electric current passes through resistor 2. It splits at this junction and goes through resistor 3 and then resistor 4 before it recombines at the end junction, and the current then finds its way into the end of the circuit. To draw an equivalent circuit, first off, there's sort of an order of events that would make this more efficient. We could think about combining 1 and 2 right away and just redrawing our equivalent circuit with 1 and 2 combined in series, and then the parallel connection of 3 and 4. We can deal with that later. Now we have 3 and 4 in parallel after the series of 1 and 2, so we could combine 3 and 4 and then combine 1 and 2 and 3 and 4. However, there's sort of a more logical, efficient way to do this. If you think about these parallel connections as being like parentheses in your calculator, there's like an order of operations, and it would be easier for us to first combine resistor 3 and 4 such that 3, 4 is in series with 1 and 2. So what that might look like is if I was to try redrawing my equivalent circuit with my voltage source, my wire, 1, I'm not going to touch that one, 2, I'm not going to touch that one yet, but I'm going to combine 3 and 4 as if they're the first thing I need to do in my order of operations. The more practice that you get with this, the better your intuition will be on which resistors or capacitors to combine when you're analyzing a complex circuit like this. But now we'll see that it will be much easier to analyze this circuit and draw it because we just have 3 resistors in series with each other, and we can connect those all and draw them as an equivalent resistor with a total resistance. And that total resistance will end up equaling the resistance of 1. Because it's in series with 2, we'll add that one, and then we'll need to add the resistance of the parallel connection of 3, 4. So first, let's calculate the parallel connection of 3, 4. That would be like 1 over 6 ohms plus 1 over 4 ohms reinverted. And for this one, we end up getting 2.4 ohms once we combine those parallel circuits, and we can now use that to calculate the total resistance, which will end up being 4.6 plus 3 plus 2.4, the number right there. And so the total resistance of this whole circuit up top can very simply be distilled down to just being 10 ohms. But now we need to calculate the power dissipated across each resistor, so we're going to need to use the electric power equation. That's either IV, I squared R, or V squared over R, depending on which variables you know for this resistor. So let's try figuring out these variables going from the bottom, our simple circuit, up to the complex circuit above. In this case, my battery outputs 10 volts into a resistor with a total of 10 ohms. So my battery's current that it outputs would be V over R, would be 1 amp. That's the total amount of current being sent out from the battery. And now if I use that number, that's what's leaving the battery. And I know that that must be going through each component in the series above, because series components have the same current. So the current flowing through resistor 1 is also 1 amp. And the current flowing through resistor 2 is also 1 amp. And the current flowing through resistor, the parallel connection of 3 and 4, is also 1 amp. And so I might need to use that number in a sec. We could also calculate the voltage drop across each of these resistors. We know the voltage supplied by the battery needs to equal the voltage dissipated by all of these resistors in the series. And so the voltage across the first resistor is just going to be 1 amp times its resistance value. It's 4.6 volts are lost across the first resistor. The second resistor has 3 volts that it dissipates. And the combo of resistor 3, 4 in parallel with each other will also dissipate the last remaining 2.4 volts. We'll see that each of those voltages adds up to the total of 10 that we had output by our battery. And so we're slowly sussing out what each of these variables are. The current and the voltage of the first resistor, the current and voltage of the second resistor separately as different variables. So we're going to calculate those. And now we know that the voltage from resistor 3 and 4 being in parallel with each other will be the same at the beginning and end points of that parallel path. The voltage at the first heart will be equal to the voltage at the second heart. The current might not be the same across each path, but we can figure that out. For resistor 3, we can determine the current flowing through it by doing V3 divided by R3. And so that is the 2.4 volts down here. That's the same voltage across 3 and 4 separately, or whether they're combined. And so that'll be 2.4 volts divided by 6. That gives us 0.4 amps down resistor 3. And to figure out the current through resistor 4, we could do a similar set of steps. We would take our 2.4 volts and divide it by 4 ohms, giving us 0.6 amps down resistor 4's path, and these both total up to be the total current that was entering this junction. Now that we know all variables that we could possibly figure out for each of these resistors, we could use any form of the power equation that's the most convenient. For example, I usually like to stick with this power is equal to I squared R. That's a very safe one to use almost all the time, because we know our current through each of our resistors, and we were given their different resistance values, so let's go ahead and calculate it. Here we see each of our power values for each individual resistor, and notice that there's really no other way of doing this. You have to basically figure out the current, voltage, or resistance of each circuit element. So here's a very useful summary of everything that we spoke about having to do with series and parallel connections. For resistors, we have our rules for series resistors and parallel resistors. You might want to copy these directly onto your equation sheet. For batteries, we have series batteries and parallel batteries. And for capacitors, we have series capacitors and parallel capacitors. Notice that all these equations are somewhat similar, so it's very easy to mix them up. But there are some patterns. For all of the series, the current flowing through each element will be the same. That's the rule for series connections. And the potential across series connections will have to be additive to the total. On the other hand, for parallel connections, we will see that the voltage is the same across each path of a parallel connection, and that the current ends up splitting in an additive type of sense in a parallel connection. Electrical meters are used to make measurements of electrical systems, and there are two common types of meters that we'll learn about. The first is called an ammeter, which measures the current flowing through an electrical system. And the way that an ammeter works is it has to be placed in series with whatever you are measuring. Basically, an ammeter is like a circuit element with an extremely low resistance, such that it lets as much current go through as it possibly can for a given small voltage applied. And so this ammeter always needs to be connected in series with whatever element you are trying to measure the current through. On the other hand, we could also think about a voltmeter, which measures the voltage across a specific circuit element. And essentially, this has a very high resistance, meaning that no current would go through it, but it would be able to measure the pushing force, the motivating factor on either side of that circuit element. So you will always connect voltmeters in parallel with whatever circuit element that you're trying to measure. And that's why we create a separate junction for the electricity to flow through when we connect a voltmeter to measure this circuit element, the voltage across that resistance. Throughout the semester, we've talked about how electrical systems can be thought of as fluid systems. Essentially, the charge in a wire is a lot like water flowing through a pipe. And so fluids are very analogous and similar to electricity. And if you understand how fluids work, you should have a decent representation of how electrical circuits work. One very complex fluid system is the human circulatory system, which pumps blood all throughout our body through differing blood vessels with different sizes and different resistances and different lengths. And the way that your heart pumps blood through your body is a lot like how a battery pumps charge through a circuit. And so there's an analogous form to Ohm's law having to do with the pressure applied to a fluid system. Essentially, the fluid resistance is very similar to the electrical resistance. And in fact, we can think about all of our fluid flow quantities that we've learned about previously to be analogous. They have an analog or a similar type of variable in an electrical sense. The charge moving through a circuit is a lot like the water, the volume of fluid being moved through a fluid system. The electric current is a lot like the flow rate flowing through a fluid system. The voltage that is applied at one end to the system to the other is a lot like applying a pressure across a fluid system with a pressure difference from one end to the other. Fluids always flow from high pressure to low pressure, and charge always flows from high potential to low potential, as long as it's positive charge. And the resistance in an electrical system can be thought of as having a similar analog as a fluid resistance. So essentially, we can draw the human circulatory system as if it's a circuit diagram, where the blood vessels act a lot like resistors and the heart acts a lot like a battery or a voltage source, pumping that blood or electric charge through the system. Here, we have two different sides of our heart capable of two different biological functions, and essentially these hearts are two batteries pumping charges one way or the other throughout our body. And our body has some resistance because we have plaque in our arteries and the walls of our blood vessels are very tight, and so the blood rubs up against the walls of the blood vessels and feels some friction. So there's energy that is lost as the heart pumps this fluid through the system, and essentially this loss in pressure as blood flows through our body is a lot like a loss in potential as electricity flows through a circuit. And so each part of the circulatory system can be thought of as being similar to an electrical circuit. Each part of our body offers a different resistance for our blood flow, and sometimes our heart has to work a little bit harder and apply a greater motivating factor to move that blood through different parts of our body. And the resistance through each part of the body will be dependent on the length of that blood vessel and its area, because we know that effectively from electricity, the resistance is basically a measure of the opposition to flow, and it's based on the geometry of the system. The wider area that I have for a blood vessel, the easier it is for blood to flow through it, and so its fluid resistance would be lower for a larger area, but the fluid resistance would be greater for a longer length of blood vessel. Ultimately, the resistance in fluid flow in our capillaries is a lot like the electrical resistance in an electrical circuit, except in our capillaries, the reason why we have this resistance is because there's friction with the walls of the blood vessel. This doesn't really happen so much with electricity because the electrons all move consistently through the conductor. It's not like they drag on each other, really. They don't affect each other all that much. So there's some slight differences, but overall, we would see in a fluid system that the fluid flow rate, Q, points from high pressure to low pressure, just like the current points from high potential to low potential in an electrical system. And if we think about all these variables as being similar across fluid resistance and electrical resistance, then we can start to say something about the variables that affect the resistance to flow. And so each individual blood vessel and portion of our circulatory system contributes to the overall resistance of the system. And the more blood vessels that there are will essentially change around the total resistance of that sector or area, that region of the circulatory system. And when we do this math, we find that the capillaries at the very end of the circulatory system and the arterioles, these smaller diameter blood vessels, are ultimately what is the largest source of resistance in blood flow in our body. So here we have an example about fluid flow rate in the human circulatory system. For a person who has heart disease, plaque builds up on the inside of their arteries, ultimately constricting the flow of blood by reducing the cross-sectional area of our blood vessels. The question is, how much will the flow rate decrease if the cross-sectional area is decreased by 20%? So if we make those blood vessels tighter, how much will the flow rate change by, assuming everything else stays the same? Well, we know that the fluid resistance is ultimately based on the Arrhenius-Poiseuille law, 8 eta L over pi r to the fourth, or another way of thinking about that is 8 pi eta L divided by the area squared. And since we're talking about the cross-sectional area here, it will be more useful to talk about the fluid resistance in terms of an area, not just the radius of that blood vessel. And so we can set up two situations and determine a proportionality for these two situations. One would be with no plaque in the arteries, and one would be with plaque built up in the arteries. In situation one, the fluid resistance is just some value. It's just some arbitrary value that we can set. I don't know exactly what number to call it, but this is a proportionality problem, so we're just going to look for a ratio that relates the fluid resistance in the second situation to the fluid resistance in the first situation. We're going to try to figure out what goes in that ratio, what that coefficient is. And I don't know exactly how R1 compares to R2. That also is not clear to me yet, but I do know one thing about the area in the beginning. If I just say it arbitrarily is some area without the plaque, I know that in the second situation, the area will be 0.8 times what the area was in the first situation. Now, by taking the Arrhenius-Poiseuille law and solving for a constant set of variables and leaving all of the variables that we don't know on the other side, we can rearrange this equation and say that 8 pi eta L is equal to the fluid resistance times the area squared. We're going to remove the FL subscript just because we know this is fluid resistance for this problem. So the resistance and the area are related. As the area goes up, we expect for the resistance to go down. And that kind of makes sense for a wider opening blood vessel. It's easier to get blood in through there. But in this situation, our area will be decreasing. And so we expect our resistance to increase. And now that we know that everything on the left side is constant, we can essentially set the right side of the equation equal in the first and second points of our proportionality. That basically means R1 A1 squared should be equal to R2 A2 squared. And now if I rearrange and solve for R2, we'll see that R2 is equal to R1 A1 squared over A2 squared. And if we go ahead and plug in some of our numbers now, we can ultimately see how R2 and R1 are related. We're basically trying to solve for what's in these parentheses here, the coefficient of the ratio. So what we would do here, A1, we would just keep the same as A1 squared. But A2 is essentially 0.8 times A1. We square what's on the bottom there, I distributed that square through. And so we'll see that A1 squared will end up canceling, leaving us with just that factor of 0.8 squared on the bottom. And so we'll have R1 divided by 0.64. Or if we wanted to solve for that coefficient, we could say that the resistance in situation 2 is 1.56 times as much as the resistance was in situation 1. An RC circuit is a special type of circuit that has a resistor and a capacitor in series or parallel with each other. And essentially, this is a very special type of circuit because this circuit will charge and discharge over time. If you think about it, first we'll have this switch, a capacitor, and a resistor up in the top right, and a battery source that has positive and negative charges localized at its terminals. When I close this switch, the positive charges will begin flowing and they will collect on the capacitor plates, charging it up such that positives reside on the positive plate and the negatives will flow the other way so that negatives collect, and we have a positive Q on one side and a negative Q on the other. And as that electricity flows, whether we're tracing the positive charges moving through or the negative charges, conventionally we'll track the positive charges, as that current flows, it also goes through a resistor, and this resistor dissipates some of that energy as light and heat. So the battery supplies a voltage to the circuit that ultimately charges up the capacitor. The resistor at the same time dissipates some of the electrical energy stored up in the circuit. And so eventually there will be an equilibrium point where the capacitor is charged up at the same exact rate that the resistor is dissipating electrical energy. And we would say that this RC circuit was at equilibrium at that time. Essentially, no current was flowing one way or the other. And so the amount of time that it takes to charge up an RC circuit will depend on how fast the resistor dissipates the energy and how quickly the capacitor can get charged up. And essentially, the larger the capacitance is, the longer it'll take to charge up an RC circuit. And the greater the resistance is, the faster that energy would be dissipated and the longer it takes to charge up an RC circuit with an increasing resistance as well. Essentially, we can define a time constant for an RC circuit that says something about how long it takes for a specific RC circuit to charge up based on the values of the resistance and the capacitance. During the charging process, we imagine positive charges leaving the battery and collecting on the capacitor plate. As this charge flows and collects on the capacitor plate, charges are flowing both ways. It's like negative charges are flowing in the opposite direction of the conventional current, and the positive charges are what we really think about in most of our equations so that they can stay positive. And as this capacitor charges up, this light bulb also lights up, or this resistor gives off some energy. Eventually, a point will be reached where the resistor is dissipating just as much energy as is being stored up by the capacitor in every given amount of time, and we would say this reaches equilibrium. We can calculate the charge stored on the capacitor based on how long we allowed for the system to charge up for. The charge at some time t, charge as a function of t, would follow this exponential equation right here, where we would eventually reach some final charge on the capacitor times 1 minus the exponential raised to the minus t over RC. Essentially, this little RC right here is that time constant that I defined, and this is an exponential function that that changes less and less over time and will eventually reach some maximum value. So what you see is this red line right here is the rate at which the charge collects on the capacitor. Essentially, charge floods into the capacitor at first when it's first emptied, but then as it starts to get fuller and fuller, it's hard to stuff it full of more charges, and eventually that capacitor will store only the maximum amount of charge that it possibly could, Q max. The maximum amount of charge will be based on the voltage that we apply to the capacitor, that's from our voltage source, and the capacitance of the capacitor. Similarly, if we think about the voltage across the capacitor, initially it had no positives or negatives on the capacitor plate, so there was no potential difference, there was no voltage. The voltage started off very low and then built up over time, and the voltage increased really fast at the beginning, but then sort of levels off as the capacitor is becoming full of its charge capacity. And we could calculate the voltage across the capacitor at some time by using this equation, where the final voltage that we reach could be calculated essentially based on the voltage source that is supplying voltage to this circuit. Again, this is another type of exponential function that slows down as time progresses. However, if we think about the rate at which charge is entering the capacitor, that's what the current is in the capacitor at some given amount of time, we could calculate the current as a function of time, and we could say that the current initially would be very large. That's what you see with this dotted line. And then as the capacitor gets fuller and fuller, the current will become lesser and lesser as is entering that capacitor. And eventually, once the capacitor gets full, no current will be flowing at all. It's full. It doesn't have any more room to let any more charges into the capacitor. And so if we wanted to calculate the initial current that was flowing in the system, that could be calculable based on Ohm's law. The initial current flowing through our whole circuit will essentially be the voltage supplied by the battery divided by the resistance of our circuit. That would dictate the current flowing through this circuit because the capacitor and resistor and battery are all in series with one another. They all have the same current flowing. And so one more time, when we first close this switch like you see up here, we will see that the initial charge on the capacitor was 0, the voltage across the capacitor was 0, and the current right when we close that switch is maximized. It's as high as it's ever going to get. But then if we let this charge up for a long, long time, like until it's full, eventually the charge on the capacitor will reach a maximum value of charge. The voltage across the capacitor will reach a maximum voltage, and the current will end up being 0 at that time. So now that our capacitor is charged up, what happens if we open this switch? If I instead open the switch and prevent the flow of electricity from the battery itself, essentially all of the charges collected on that capacitor plate will recombine. They'll go back to their original starting locations. All of the negatives that collected on this plate will try to recombine with the deficiency of negative charges that left the negative terminal of the battery. And so this capacitor is full of charge, and there's a resistor down the line a little bit. And so the capacitor begins discharging, letting its charge and electrical energy flow through the system in the opposite way that it was when it was charging. And that current will be sent out from the capacitor and dissipated. The energy will be dissipated by this resistor. So in this way, the capacitor essentially acts like a short-term battery. The battery was a big voltage source. We applied it to the capacitor. It charged up the capacitor a little bit. And then the capacitor begins discharging, keeping our resistor on, even though we opened the switch. So it's like a capacitor can store energy for a short-term amount of time. So we would find initially, right after we open the switch, that the charge on the capacitor is some initial charge value, essentially the max value that we reached in the last slide. The voltage across the capacitor is some initial voltage value, and the current initially flowing will be a lot. Right when we open that switch, all of the charge is going to try to flood out of the capacitor as fast as it can, because negatives don't want to be near each other on the negative plate, so they fly out of that negative plate and go through the resistor and ultimately create light and heat energy to dissipate the energy that was stored across the capacitor when it was charged up. And as it discharges, we expect for the charge on the capacitor to decrease. And it's going to decrease a lot in the beginning when there's a lot of charges there, and then it will sort of peter out or level off the rate at which the charge is leaving. And this would be thought of as an exponential decay function, like you see right here. Similarly, the voltage across the capacitor will also be a function of time, where the voltage decreases really rapidly at first, but then eventually asymptotically approaches a 0 volt point. And as time goes on, we can also calculate the current flowing out of the capacitor and through the resistor. That current will be maximized initially. The charge will flood out of the discharging circuit, but eventually it will level off asymptotically until it reaches an equilibrium steady state where the current is 0. So let's take a look at an RC circuit in a biological system. Here we have an axon, which is essentially like a wire in the nervous system that connects different neurons. It takes an electrical signal from one point of the brain and sends it down a nerve. And so this axon acts a lot like a discharging RC circuit. As an electrical signal is sent out from a neuron, it goes through this axon, and it kind of gets like boosted every time that it goes past each of these little nodes. There's a discharging type of electrical boost that it gets to make sure the signal makes it all the way to the end. And that discharging happens through a sheath that is coated around the axon. It has a capacitance and a resistance that is required to be overcome as it sends that electrical signal out and discharges. So We're given some values and asked to solve for the time constant. Solving for the time constant is rather straightforward. Tau should be equal to R times C, but we want to make sure we're careful about the different units that we have here. Here's 40 mega ohms. That means 40 times 10 to the 6 ohms. And the capacitance is given in picofarads. That's 2.5 times 10 to the minus 12 farads. And when we multiply this together, we end up getting something like tau is equal to 1 times 10 to the minus 4 seconds. Maybe if we wanted to make that into more of a useful time scale, that'd be like 0.1 milliseconds, or perhaps something more like 100 microseconds. And this is a time scale that seems reasonable for certain biological functions. So this charging and discharging RC circuit has an exponential type of behavior. As it charges up, it rises toward a maximum value and then slows down as it approaches that maximum value. And as it discharges, it exponentially decays. It decays really fast at first. Its rate is very large, but then that rate also gets lesser and lesser as time goes on. This is called an exponential process, and there are basically 3 types of exponential processes for very common sets of problems that we deal with. First, we have exponential growth, which essentially says that the amount of stuff that we originally have will affect the growth rate, and the more that we have in the beginning, the greater the growth rate will be after some time period. This is the case for population growth, outbreaks and epidemics, nuclear chain reactions, and compound interest. Another type of exponential process is exponential rise to a maximum value. Here you'll see that this is a little bit like exponential growth. It is increasing the amount of quantity that we're measuring in whichever system this is, but it slowly decreases the rate of change as time goes on, whereas with exponential growth, it has a runaway growth pattern that never decreases its growth rate. This is the example of what we see for a charging RC circuit, or perhaps maybe like a bucket that has a hole in the bottom and we're trying to fill it up, or like how drugs are released in our human body and how the concentration of those drugs builds up over time as our body can process them. The last type of exponential process that we will look at is called exponential decay, which essentially means that we lose a lot of some quantity rapidly in the beginning, but then the rate at which we are losing some quantity decreases over time. So we start off at some large maximum value, and as time progresses, our quantity gets lesser and lesser, but the rate at which it changes is based on how much stuff we originally have at the beginning of some time interval. And this would be the situation for a discharging RC circuit. The charge leaves the circuit really fast in the beginning, but then it takes a while at the end to get rid of all of the charge. This is also the same as how drugs are cleared in our bloodstream, or how nuclear elements experience radioactive decay. Exponential growth is a process where a quantity increases its value proportionally to how much the original quantity was. So essentially, this is a runaway growth type of behavior where the rate at which some quantity grows with respect to time is based on a rate constant or a time constant tau. So here in these equations, Q is not necessarily the charge. For electrical systems that might work, but Q is just a general variable used to track some quantity of interest. It could be dollars in your bank account. It could be the number of COVID cases during a COVID breakout. So this number of cases for COVID, for example, we could calculate that at some time based on the initial amount of cases at that time interval times by some exponential growth factor that is growing positively with respect to time. And this time constant will essentially dictate the rate at which that exponential growth takes hold. We can define a rate constant K, which is ultimately related to the time constant of the system. And in the case of exponential growth, we often will define something called the doubling time, which is essentially the time that it takes this specific system to double from its initial value. And that'll ultimately be based on the rate constant or time constant for the specific situation. And if we were to think about specifically public health and COVID, the growth of COVID cases is balanced by the negative effect of resolving COVID cases. And so normally in real situations, we'll have a competing effect between exponential growth factors and the resolution or negative growth of those relationships, that behavior. And so the total rate constant would be a blend of the positive rate constant. That would be like the transmission rate of new cases of COVID coming up, minus the rate at which cases are being resolved. And for many public health situations, the best way to minimize the overall amount of some quantity is to reduce the rate at which the positive growth is occurring. Essentially, by reducing the positive rate constant, we can curb this growth and slow it down, which is essentially what happened during the COVID-19 pandemic. When we first experienced several waves of COVID, we saw periods of exponential growth in the number of cases that rose. And so as more cases cropped up, more people started getting sick and the rate started to run away. But through public health measures like social distancing and masking, we were able to reduce the positive growth factors and reduce the positive growth rate to ultimately curb that spread of that pandemic. Another type of exponential behavior is exponential growth to a maximum value. This is sort of like exponential growth, but different, because this is where a quantity increases rapidly at first, but then levels out the rate at which it is increasing over time. Essentially, we are required to have a constant input source for this and a constant output source for this, but the input needs to affect the rate at which the output is being taken care of. So for example, let's think about a leaky bucket. That's like a bucket that I'm trying to fill with water by dripping water in from the top, but it's also slowly leaking out the bottom. You'll find for this situation that as I fill up the bucket more and more, it will drain faster and faster. And so there will be a competition between how quickly I can fill in the bucket with an inflow rate versus the rate at which the quantity is leaving the bucket, the outflow rate. And I need to somehow balance these competing factors until I can achieve an equilibrium state. Because the flow rate out will increase as more and more water's in there, because the pressure is greater at the bottom of the bucket, the more water there is in there, that means we will have growth to a maximum. And that growth to a maximum sort of has a shape like what you see down here in the bottom right. And we would see that if we thought about the water volume as our Q, our quantity that we're tracking, we could say something about the rate at which the volume changes as being a balancing between the inflow rate and the outflow rate, the positive growth factor and the negative growth factor. And what we would see for the equation that models this growth to a maximum, you will always have a 1 minus some exponential term. Essentially, we'll have a maximum value minus some term that changes with respect to time and gets smaller and smaller with respect to time. This e to the negative power is like an exponential decay. So we will have a maximum minus a decaying function until we eventually reach a maximum value, essentially. And so while I chose to use this bucket as an example of a growth to a maximum, this is also the type of behavior that we see in a lot of other physical systems, including the charging of an RC circuit. Lastly, we have exponential decay, which is a process where a quantity decreases at a rate proportional to how much the quantity value is at some time interval. For example, in radioactive decay of radioactive nuclei in some type of nuclear process, the rate of decay is very large at first. When I have a lot of that substance, it breaks down very quickly and gives off a lot of radiation very quickly. But over time, the quantity of those nuclei in that sample decreases, and the rate at which that nuclear reaction takes place also decreases based on how much stuff we have in there. And so in this case, our Q that we're choosing to track is like the number of radioactive nuclei. It's just a quantity, and it will be affected with respect to time. And the way an exponential decay function looks is it will always have e raised to the negative power of t over the time constant. So you can see how the exponential growth, rise to a maximum, and exponential decay are all sort of similar. They all have an exponential in there, but the format of each of those different behaviors has a different math relationship that's slightly different. Maybe a negative here or a positive there or a 1 minus something. So you'll want to be able to recognize exponential growth, exponential rise to a maximum, and exponential decay, and be able to see the equations, maybe not even for an electricity application, maybe for a compound interest application. These are all still ideas that would hold true whether we're looking at a physics problem or some other type of problem. In the case of exponential decay, instead of labeling a doubling time, we could label a half-life time, which is essentially the amount of time that it takes for the original value that we have at the beginning of some time interval to be cut in half. And this would ultimately be based on the time constant or the rate constant of the system. So let's try an example of exponential processes in a biological application of medicine. When morphine is administered through an IV, it is available to the body and then the body begins clearing it. And so initially we have a lot of some quantity being added to our body and our body begins filtering it out. And so we will filter that large quantity quickly at first, but then as there's less stuff over time, we expect for the rate at which our body filters it to also decrease. So this is indicative of an exponential decay behavior. Another indicator of that is that you were given the half-life time, and half-life time applies to exponential decay functions. So the question is, how long will it take until the concentration has dropped to 10% of its initial value? Let's just think about this as a general exponential type of behavior. Here, let's get some ideas out of the way. Q is not our charge. Q is going to be some quantity of interest, and in this case, I'm going to label it as the concentration of morphine in the body. We give you a dose of morphine and there's a lot at first and your body begins to filter it. And so we would expect for it to start at a maximum value. And then as we're thinking about the concentration in your body, it will change over time and it will experience an exponential type of behavior. And so Q is our concentration of morphine. And in the beginning, we just have some value of Q0. That's our initial concentration. And in the end, we are going to end up having a concentration in our body that is based on that original value. Q final will end up being 10% of what it was initially. So it's got a factor of 0.1 times the initial value. Well, we know for an exponential function that the quantity as a function of time is related to the original value times e to the negative t over tau. That's true for any exponential decay function, by the way. And so we were given the half-life time, and we want to recall how the half-life time relates to the time constant of this system. The half-life time is the time constant times the ln of 2. And so if I take my half-life time and divide it by ln of 2, I should be able to figure out the time constant for this particular process. And so for the time constant, I end up getting 3.6 hours. Whether you keep that in hours or seconds is fine for these types of problems. Let's just keep it in hours for now to try to keep it consistent, and we'll track our units throughout the calculation. So we essentially need to rearrange this equation and solve for t. We're asking how long will it take? That means t is equal to question mark for this problem. And rearranging an equation with an exponential in it can get a little tricky, so follow me on this one. First, we would divide Q0 over to the other side, and we would get Q at some time divided by Q0 is equal to e to the negative t over tau. And to undo an exponential here, I need to take the natural log of both sides of the equal sign. I need to take the natural log of this side, and I need to take the natural log of the right side. And when I end up doing that, that just gets rid of my e on the right side and leaves the natural log on the left side. And I know my tau value, so I can multiply it over. And I now have a relationship for the time that it takes for the drug concentration to reach 10% of its original value. So we can plug in our numbers and go ahead and solve. In this case, the quantity at some time is just 10% of what it was originally. So I can plug in 0.1 Q0 divided by Q0. I don't know what that number is, but I know that it'll end up canceling. And I better make sure I don't forget that negative, because we do want our time to end up coming out positive. And when I do this math, it does come out as positive 8.3 hours or somewhere around there. So for that dose of morphine, it's going to take about 8 hours for it to be reduced to 10% of its original value based on this half-life time. Circuits was our attempt to take everything that we've learned so far in physics and put it together for a useful application in electricity. Next, we'll be moving on to magnetism, which can also be a little bit tricky, so make sure you understand these equations before moving on. Thanks for paying attention. I'll see you in the next one.